So hi everybody, I am Guido Szabó from Ericsson Research Hungary, and I would like to show my presentation about information gain regulation in reinforcement learning with the digital twins level of realism. Let me share my screen. As an introduction, and very briefly, I would like to emphasize that Industry 4.0 is very much about smart manufacturing, delivering personalized products, data analytics, and shorter time to market. Cyber physical systems, it's with remote controlling, it's very much on the table. And the channel between these controllers and the controlled environments can be 5G connectivity. In a regular Industry 3.0 setup, the robotic working cell is controlled, for example, with PLCs. They are doing the very same job 24/7. And the robot control is it's much about that there is a robotic arm with power, servo control, and all commands connected with the controller box. And the controller box does all the trajectory calculations, kinematics, and this controller box is usually programmed by, for example, USB key is switched into them, which contains all the robot programs which has to be executed, and it's done 24/7 all year long. Very rarely it changes the program itself. In Industry 4.0, there are new hardwares in the setup. There can be an edge cloud with predictive maintenance, position and control over virtualized PLCs. There can be sensors all around the system, and then there can be a radio, for example, to collect data from the sensors. The robotic control in the Industry 4.0 scenario is that there is an edge cloud, and the over robot cell scheduling is done in the edge cloud, and the controller, which was used to do the low-level control of the robot arm, it still does the same, but the update or the trajectory is calculated much more frequently. Position commands are sent about, for example, every 10 seconds to the robot controller. If we go for this future factory for robot control, what can happen is the edge cloud does the trajectory calculation and all the kinematics instead of this controller command controller box. Practically, it happens to be only for power and proxying the commands towards the robotic arm. And so velocity commands are sent per servo to the robotic arm in a much higher frequency. For this UR5, it happens to be 125 Hertz. And so when there is this kind of pit control, there is velocity command going to the actuators, and there are status messages coming from the robotic arm, then the network quality is very important. So if there is a glitch in the network, there will be a glitch in the motion of the robotic arm. So we need ultra reliable, low latency communication to ensure the good, smooth movement of the robotic arm. But do we need this URL state connection 24/7 for a robot cell? In 2018, we said that maybe not. So the wireless control can be taken into action at robot cell programming level. And we propose the quality of control aware wireless resource allocation algorithm that is based on the categorization of the robotic arm movement phases to high and low quality of control requiring movements, saying that the various actions of the robot can be divided into important and accurate movements and to unimportant movements, and you only have to ensure good quality for the robot or good channel to the robot when it do some very accurate movement. About And it was then manual, and we said that about 50% of the radio time that requires URLC only, and the robot cell productivity does not affect it if we relax these requirements of URLC. And so at that time, we have done everything manually. So the quality of control awareness is wired into the robot control. What we would like to achieve is that move this this tagging to be done automatically into the radio and be used automatically by the network. And so forth, from that point, there is no need for the robot integrator to modify anything on the original control. A good candidate algorithm to do that is, for example, reinforcement learning, one type of AI algorithm that we can use there. In reinforcement learning, we need an environment where our agent does certain actions. We try to build up a policy to use or decide or do smart actions, and the environment responds to it with some kind of reward, and also the state where this action has been taken is also noted. And this is with an iterative process, the agent tries to, or the learner algorithms try to refine the policy that the agent will do. If we have the environments that can be done or can be used for robotics, the most beneficial one, if we go with fully hardware realized environments, the benefits of it is very easy to transfer policy from from the learned or from during training to the testing phase. Main disadvantage is that it's very expensive and very slow. So for example, if Google had this paper that robots try to learn grasping by sharing hand-eye coordination, and they built everything with hardware. They'll have dozens of robots doing the very same stuff, collecting samples for the reinforcement learning algorithm. If we go with a fully simulated scenario, the most benefit is that it's cheap, it scales very well. We can use a cloud infrastructure and run the simulations there. But the main disadvantage is that if we would like to transfer this policy that is learned from fully simulated scenario into a hardware realized one, it's very difficult to transfer this policy. It may behave differently. So to overcome this issue, we had a paper in 2019 about a network digital twin, which means something in between a solution between the fully hardware realized and the fully simulated one. It provides very realistic training environment, still much cheaper than the fully hardware realized one, but it does not scale well, so we need expensive robotic arms still to do so. So the solution for this issue, for the scaling, is that we introduced a custom reinforcement learning algorithm in which we said that for the environments and for the workers which testing our policies and collecting samples, these trajectories for the learners, they are aware of the custom environment that they were running it. And we said that this custom environment can contain that kind of level of realism information in which they were executed. So for example, in this digital twin, a mostly hardware realized environment has a high level of realism, while a completely simulated environment has a lower level of realism. Also, this refers to the robot cell deployment option, but this can be also used for this radio connectivity option, and a fully hardware realized 5G URLC device has a high level of realism compared to the, for example, a Linux traffic control solution when all delay and jitter is emulated. So we tag the information of the trajectory where they were, the environment where they were executed and collected, and the learner can consider the environment information and weights the samples accordingly. I would like to show this for you in action. So in this demo, what you see here is that this automatic categorization of the robotic arms, which is done by an agent using reinforcement learning, and we used one head node and seven workers collecting samples, and we use this open source RNLib library for the reinforcement learning. We use the ARIAC 2017 environment. It's a competition environment. It's about pick and place actions, and the ARIAC requires participants to complete series of steps centered on industrial scenario, just based around collecting kits and shipping on AGVs. And the agent samples the environment periodically, and we provide position, velocity, effort, and gripper status for the robots. The action is selected from the discrete action space to switch high or low quality of control mode in every second. What you see here is that colored lines show the currently used quality of control channel. Blue means low quality of control, red means high quality of control. We want to maximize the amount of blue lines. And this is the speed up version of the learning. So the colors of the spheres show the progression over time. What you see is this 1000 times sped up environment. Blue means higher latency and low quality of control, and the goal is to maximize the amount of blue spheres. A sphere gets bigger whenever the robotic arm samples from that particular position, and in places where more precise movement is required, high quality of control is dominating. Therefore, the spheres there are more reddish, and the transitional places where the robot moves a straight line, it's more bluish. You can see results after 1 day of continuous learning here, some AI or KPIs here. And we can say that about after 300 episodes, the agents try to pick low quality of control phases approximately 70% of the time. And here is the final learn policy, what you see here. And going back to my, we need ultra reliable low latency communication, approximately 30% of the total radio time. And in conclusion, is we can say that in this paper we proposed an architecture in which the radio access control is performed automatically to minimize the utilized radio resources while still maximizes the production KPIs of the robot cell. And to achieve this, we introduced this kind of digital twin and custom environment tagging, and we achieved that about 30% of the total radio time can be used for ULC, and the other part can be relaxed, and we still achieve high productivity KPIs. Thanks for watching this presentation.